Welcome to the birthplace of AI. To understand this era, you have to realize that computers back then weren't the sleek slabs of silicon we have today. They were room-sized monsters made of vacuum tubes, and programming often meant physically moving cables on a patch bay. Before there was software, there was a mathematical abstract. Warren McCulloch, a neurophysiologist, and Walter Pitts, a homeless, self-taught logician prodigy, asked a wild question. Can we model the human brain using binary logic? They designed a highly simplified model of a biological neuron. It took binary inputs, 0 or 1, multiplied them by preset weights, and if the total passed a certain threshold, it fired an output. The math: if the inputs are x1 through xn, the neuron fires when the weighted sum passes the threshold, theta. The catch: this neuron could not learn. If you wanted it to solve a problem, a human mathematician had to manually calculate and hard-code the weights and the threshold. The significance: it proved that a network of these artificial neurons could, in theory, compute any logical function, like and, or, and not. They proved the brain was a computer. Alan Turing was tired of people debating definitions of thinking. He published a seminal paper, Computing Machinery and Intelligence, which completely bypassed the philosophical weeds. He introduced the imitation game, now called the Turing test. Instead of asking, can machines think, he asked, can a machine convince a human that it is human through text? And in the exact same paper, Turing predicted machine learning. He argued that instead of trying to program an adult-level mind from scratch, it would be much easier to program a child mind and subject it to a course of education, training, to let it learn on its own. While working at IBM, Arthur Samuel wanted to prove that computers could do more than just crunch payroll data. He decided to teach an IBM 704 mainframe to play checkers. Samuel didn't just hard-code winning moves, he wrote a scoring function that looked at the board state, the number of pieces, kings, center control, and calculated the probability of winning. The learning part: he made the computer play against itself thousands of times. Every time it lost, it adjusted the importance, the weights of those board features. Eventually, the program beat the champion of Connecticut. Samuel officially coined the term machine learning in 1959. He proved that a machine could outperform its creator at a specific task. If McCulloch and Pitts built the blueprint, Frank Rosenblatt built the actual machine. This is the official grandfather of modern deep learning. The Perceptron was an actual physical machine, the Mark I Perceptron containing 400 photocells, an early camera connected to artificial neurons. Most importantly, it could learn its own weights automatically. If the Perceptron guessed an image wrong, an electrical signal was sent to small motors that physically turned dials to adjust the weights up or down until the machine got the answer right. The media went wild. The New York Times reported that the Navy-funded project would soon result in an electronic computer that will be able to walk, talk, see, write, reproduce itself, and be conscious of its existence. The massive hype of the 1950s hit a brick wall in 1969, courtesy of MIT professors Marvin Minsky and Seymour Papert. They published a mathematically brutal book titled Perceptrons. In it, they proved that a single-layer perceptron was fundamentally incapable of solving the XOR, exclusive or logical function. A single-layer perceptron can only draw a straight line to separate data. If you plot an XOR gate on a graph, you cannot separate the ones from the zeros with a single straight line. You need a curved line or multiple lines. Minsky and Papert proved that to solve complex problems, you needed multi-layer networks. However, they also claimed that calculating how to adjust the weights across multiple layers was mathematically intractable. Governments and universities panicked, assuming neural networks were a dead end. Funding evaporated overnight, plunging AI into its first major winter. By 1970, the funding was gone, the labs were empty, and neural networks were declared a dead end. But in the shadows of that winter, a handful of rebels kept working on the one problem Minsky called impossible. Next time, the underground years and the algorithm that finally broke the XOR wall. Welcome to the AI underground. While the mainstream computer science world spent the 1970s and 80s focusing on expert systems, massive, hand-coded if-then rulebooks, a small group of defiant researchers continued working on neural networks in the shadows. They were determined to prove Marvin Minsky wrong and break through that XOR wall. Minsky's critique was right about one thing. To do anything smart, a neural network needed hidden layers between the input and the output, but nobody knew how to train those hidden layers because you couldn't directly see their errors. Enter backpropagation, the single most important training algorithm in AI history. The backstory: Paul Werbos actually invented it in his 1974 Harvard PhD thesis, but because of the AI winter, nobody noticed. In 1986, David Rumelhart, Jeffrey Hinton, and Ronald Williams published a paper that popularized it, making the world finally pay attention. How it works: in the forward pass, data goes into the network, guesses are made, and the error is calculated at the end. In the backward pass, the algorithm uses calculus, specifically the chain rule, to work backward from the output layer to the very first layer, calculating how much each specific weight contributed to the total error. It then tweaks each weight in the opposite direction to reduce the error. This completely vaporized the XOR problem. Suddenly, we could train deep networks with multiple layers. While Western researchers were obsessed with logic, Japanese scientist Kunihiko Fukushima was obsessed with biology. He wanted to mimic how the human eye and brain see. He looked at the Nobel Prize-winning work of Hubel and Wiesel, who discovered that the visual cortex of cats uses a hierarchy of cells. Some cells look for simple edges, while others combine those edges to see shapes. Fukushima built the Neocognitron. It introduced two revolutionary layer types: S cells. Simple cells extracted local features like a diagonal line. C cells, complex cells, allowed for shift invariance, meaning the network could still recognize a shape even if it moved to a different corner of the image. The Neocognitron didn't use backpropagation yet, but its architecture was the exact blueprint Yann LeCun would use a decade later to create the first successful convolutional neural network. Up to this point, neural networks were completely feed-forward and amnesiac. You gave them an input, they gave you an output, and they immediately forgot everything. That's fine for photos, but useless for text, music, or time series data, where context matters. In 1982, John Hopfield created a network that could store and recall memories, a fully connected network that acted like human associative memory, like hearing a song lyric and remembering the whole song. In 1986, Michael Jordan, the computer scientist, not the basketball star, and Jeffrey Ellman introduced the idea of feedback loops. Instead of information flowing strictly left to right, the output of a hidden layer at one time step is fed back into itself, as part of the input for the next time step. For the first time, AI had an internal state, a form of short-term memory. It could process a sentence word by word, carrying the memory of the previous words along with it. The plot twist: by the late 1980s, these rebel researchers had solved the major theoretical problems. They had backprop to train networks, the blueprint for vision, and the blueprint for sequence memory. But they hit a massive roadblock. The computers of the 80s were painfully slow, and the datasets were tiny. The math worked perfectly on paper, but in reality the networks were sluggish and couldn't scale. They were waiting for the hardware to catch up. Next time, the 1990s, how Yann LeCun made these concepts practical, and how recurrent networks almost died from a fatal mathematical flaw. Welcome to the 1990s. This was the era of grunge music, the birth of the consumer internet, and a massive identity crisis for artificial intelligence. Researchers had the mathematical frameworks for convolutional and recurrent networks, but computers were still too weak to run them at scale. This forced the AI community to do two things: design highly specialized architectures that could maximize efficiency and pivot toward rigorous, non-neural statistics. Yann LeCun, a French researcher working at AT&T Bell Labs, looked at Fukushima's Neocognitron and thought, what if we train this using backpropagation? In 1989, he built the prototype, and by 1998 he had perfected LeNet 5. It was a masterclass in efficiency, introducing the core components of every modern computer vision AI. Convolution layers. Instead of looking at an entire image at once, which takes too much processing power, a small mathematical filter called a kernel slides across the image to detect local features like edges, corners, and curves. Pooling layers. These downsampled the image, shrinking its size while keeping the most important visual information. And it worked in the real world. LSTM 5 was deployed commercially, reading handwritten zip codes on envelopes and numbers on bank checks. By the late 90s, it was reading up to 20% of all checks in the United States. While LeCun was succeeding with vision, researchers trying to build deep text and speech models hit a catastrophic mathematical brick wall. Remember, backpropagation uses the chain rule, multiplying gradients layer by layer, time step by time step. The problem, if the weights in a network are small, less than 1, multiplying them over and over causes the gradient to shrink exponentially. If a sentence is 50 words long, the error signal has to travel back 50 time steps. 0.9 multiplied by itself 50 times is about 0.005. The signal vanishes. The network completely forgot what happened at the beginning of a sentence. Recurrent networks were effectively useless for anything longer than a few words. Two German researchers, Sepp Hochreiter and Jürgen Schmidhuber, set out to fix this memory loss. They invented the long short-term memory network, the LSTM. They replaced the standard simple neuron with a complex memory cell. Think of it like a mini hard drive, with a constant error carousel that lets information flow through time without being multiplied down to zero. LSTMs introduced 3 mathematical gates: a forget gate, deciding what information from the past to throw away; an input gate, deciding what new information to store in the cell; and an output gate, deciding what information to output next. LSTM solved the vanishing gradient problem. This architecture became the undisputed king of speech recognition, language translation, and text-to-speech for the next 20 years, eventually powering early versions of Siri and Google Translate. Despite the success of LSTM and LSTMs, neural networks were incredibly finicky, slow, and required a lot of art to tune. The broader computer science community grew frustrated. In 1995, Vladimir Vapnik and Corinna Cortez popularized support vector machines. Instead of trying to mimic the brain, SVMs used elegant, rock-solid linear algebra to find the optimal boundary separating different classes of data. For most of the late 90s and 2000s, if you submitted a paper about neural networks to an AI conference, it was often rejected. The industry shifted heavily to SVMs, random forests, and Bayesian statistics. Only a handful of stubborn researchers, Geoffrey Hinton, Jan LeCun, and Yoshua Bengio, often called the Deep Learning Mafia, kept the neural network flame alive. They were waiting for the world's hardware to catch up to their math. Next time, what happened when their math finally met modern video game graphics cards? Era 4, the deep learning boom. Welcome to the Big Bang of modern AI. Between 2012 and 2016, machine learning went from an academic subfield to a multi-billion-dollar industrial revolution. This boom happened because 3 things finally collided: the math from the 80s and 90s, the explosion of internet data to train on, and the discovery that NVIDIA graphics cards, originally built for rendering video game graphics, were accidentally perfect for running matrix multiplications in parallel. In 2012, the AI community was hyper-focused on the ImageNet challenge, a competition to see if software could accurately categorize 1.2 million high-resolution internet images into 1,000 different categories. Dogs, boats, apples, traditional statisticians were hitting a wall, struggling to cross 74% accuracy. Then came Alex Krzyzewski, Ilya Sutskever, and their PhD advisor Geoffrey Hinton, the godfather of AI, at the University of Toronto. Their weapon, AlexNet, a massive 8-layer deep convolutional network. They broke from tradition by coding the network to run on 2 consumer NVIDIA GTX 580 graphics cards, and they swapped out traditional sigmoid math for a much faster activation function called ReLU FFX, equals the maximum of 0 and x. AlexNet didn't just win the competition, it absolutely pulverized the field, beating the runner-up by an unprecedented 10.8 percentage points. The tech world had a collective holy shit moment. Within months, Google, Baidu, and Microsoft pivoted their entire research budgets away from classical statistics and into deep learning. Until 2014, deep learning was mostly used to classify data. Is this a picture of a cat? It couldn't create anything new. Ian Goodfellow changed that over drinks at a bar when he conceptualized the generative adversarial network. Instead of training one network, you train 2, playing a high-stakes game of poker against each other. The generator tries to create fake data, like a fake human face, from random noise. The discriminator inspects the image and tries to guess if it's a real photo or a fake generated by its partner. They train together, the generator gets better at lying, and the discriminator gets better at catching lies. GANs allowed AI to become generative. Suddenly, computers could generate hyper-realistic faces, synthesize artwork, and upscale low-resolution videos. It was the birth of deepfakes and of AI imagination. By 2015, researchers knew that deeper is better. However, if you tried to stack more than 20 or 30 layers in a network, the mathematical errors would get lost in transit, and the network's accuracy would actually drop, a problem called network degradation. Kaiming He, Xiangyu Zhang, Xiaoqing Ren, and Jian Sun at Microsoft Research introduced ResNet, residual networks, with skip connections. Instead of forcing data to pass through every single layer sequentially, the architecture allowed the network to skip layers entirely if they weren't adding value. This solved the degradation problem. ResNet successfully trained a network with 152 layers, 8 times deeper than anything before it, and won the 2015 ImageNet challenge with a 3.57% error rate, officially outperforming human eyesight on the dataset. Skip connections are so foundational, they are used in every GPT model today. For decades, computer scientists believed the ancient Chinese board game Go was impossible for an AI to master. Go has more potential board configurations than there are atoms in the observable universe. It requires intuition, not just calculation. DeepMind combined deep convolutional networks to look at the board and predict the best moves, with reinforcement learning, letting the AI play against itself millions of times and tree search. AlphaGo challenged Lee Sedol, the 18-time world champion, in a televised 5-game match in Seoul. AlphaGo won 4 games to 1, playing creative, bizarre moves that defied 3,000 years of human Go strategy. It proved that deep learning could develop human-like intuition and solve complex strategic problems that humans couldn't map out explicitly. By 2016, deep learning was king, but it had a massive bottleneck. Computer vision was thriving, but language was lagging behind. LSTMs were still reading books word by word, making it impossible to train them on the whole internet. Next time, how a team of 8 Google researchers blew up the entire landscape. Era 5, the Transformer Revolution. Welcome to the architectural shift that defines the modern world. By 2017, natural language processing was trapped in a bottleneck. LSTMs were the best tool available, but they processed text sequentially, word by word. If a model was reading a 500-page book, it couldn't read page 500 without processing pages 1 through 499 first, which meant you couldn't train them across thousands of GPUs simultaneously. Then, a team of 8 researchers at Google decided to throw out recurrent loops entirely. In June 2017, Google researchers published a paper with a deceptively simple title, "Attention is All You Need." They introduced the transformer, an architecture that abandoned recurrent networks entirely, relying instead on a mechanism called self-attention. Instead of reading text from left to right, a transformer looks at an entire sentence or an entire document all at once. For every word in a text, the self-attention mechanism calculates a mathematical score, representing how much attention it should pay to every other word in that text. The math maps queries, keys, and values. Attention equals the softmax of Q times K transposed, divided by the square root of the key dimension times V. And here is why it was a game changer. Because it processes everything simultaneously, it is massively parallelizable. Suddenly, AI labs could take thousands of GPUs, link them together, and feed them the entire internet, Wikipedia, digitized books, Reddit threads in weeks, rather than decades. Once the transformer was unleashed, the AI world split the architecture into 2 distinct philosophies for handling language. In 2018, Google introduced BERT, the reader, an encoder-only model. It looked at the words to the left and to the right of a target word simultaneously to understand deep context, best for comprehension, sentiment analysis, and upgrading Google search to understand the nuance in your queries. OpenAI took the opposite path with GPT, the generative pre-trained transformer, the writer. A decoder-only model, it looked strictly from left to right, and its only job was autoregressive prediction. Given this sequence of words, what is the most statistically likely next word? Best for generating fluid, creative text. For a couple of years, people weren't sure how far the transformer could go. Then, in 2020, OpenAI published a paper on scaling laws, proving that if you scale up a transformer model, giving it more parameters, more data, and more compute, its performance doesn't just improve linearly. It unlocks entirely new, unprogrammed capabilities. To prove it, they built GPT-3. GPT-1 had 117 million parameters, GPT-3 had 175 billion. And it shocked researchers. It wasn't just completing sentences. It was suddenly able to write functioning Python code, translate between languages it was never explicitly taught to translate, and solve basic logic puzzles. It proved that brute force scaling creates a form of artificial intelligence. While GPT-3 was brilliant, it was hard for regular people to use. If you didn't prompt it perfectly, it would just ramble or mimic internet toxic waste. It was a raw engine looking for a steering wheel. OpenAI solved this using a technique called reinforcement learning from human feedback. Human trainers graded the model's outputs, teaching it how to behave like a helpful, polite, and safe assistant rather than a chaotic text predictor. On November 30th, 2022, they put a simple chat interface onto this fine-tuned model and released ChatGPT to the public for free. It became the fastest-growing consumer application in history, reaching 100 million monthly active users in just 2 months. The world realized that AI was no longer a back-end tool for tech companies, it was an interface for human thought. Next time, the final chapter, the current state of the art, how these models became multimodal and shifted from predicting text to deep reasoning. Era 6, Frontier Scale. Welcome to the cutting edge. By 2023, the tech industry realized that just scraping more raw web text to make models bigger was hitting a wall of diminishing returns. The highest quality data on the internet was running out. To break through, AI labs had to pivot from teaching AI what to say to teaching AI how to think. This is Era 6, Frontier Scale, and Reasoning Models. Before 2023, if you wanted an AI to look at an image and write a caption, you had to glue 2 different AIs together, a computer vision model and a language model. Then OpenAI with GPT-4 and Google with Gemini built natively multimodal transformers. They figured out how to convert images, audio, video, and text into the exact same mathematical language, vectors, from day one. The model doesn't see an image and convert it to words. It processes visual pixels and textual words interchangeably within the same neural network. This allowed AI to analyze complex medical scans, read financial charts, design websites from a napkin sketch, and understand voice intonation in real time. Historically, large language models were autoregressive next token predictors. If you asked a standard model a highly complex math question, it would blurt out the first word immediately without pausing to plan, like a human speaking without thinking. In late 2024, OpenAI launched its O1 model, codenamed Strawberry, followed by open-weight equivalents like DeepSeek R1 in early 2025. This introduced a brand new axis of AI scaling, test-time compute. Instead of generating an answer in a single mathematical pass, the model generates a hidden internal chain of thought. It talks to itself, drafts plans, double-checks its logic, discovers its own mistakes, and corrects them before it outputs a single word to the user. And instead of just rewarding the AI for getting the final answer right, researchers used reinforcement learning to reward the AI for every correct step in its logic. For a decade, an AI's power depended on how much compute was used to train it. Now, an AI's power also depends on how much compute you allow it to use to think during the question. This unlocked superhuman performance in advanced mathematics, coding, and scientific research. We are currently living in the agentic shift. AI has transitioned from a passive chatbot waiting for a prompt to an autonomous agent that can be given a high-level goal and left alone to accomplish it. Models can decide on their own to execute code, search the web, or access external databases to solve multi-step problems. Time horizons have expanded. In 2023, an AI task took seconds. Today, developer agents operate over hours, days, or weeks, navigating massive, messy codebases, writing tests, debugging failures, and deploying full software features with minimal human intervention. And complex systems are no longer driven by a single AI. Companies deploy coordinated teams of specialized subagents. One agent browses the web, another screens the data for errors, a third writes the report, and a manager agent reviews the final product. The map is complete for now. You have traveled all the way from a two-variable chalkboard equation in 1943 to autonomous digital entities capable of complex reasoning and tool use. 80 years, 6 eras, one idea, let the machine learn. This has been How Machines Learned. Thanks for watching.